Intel has designed several processor technologies that enable parallel processing when running multi-threaded applications or multiple applications simultaneously. The first, Intel hyperthreading technology, enables two threads to be processed in a single processor core, allowing partially parallel execution, whereas traditional single-threaded processors could only process one thread at a time. Next was the dual-core Intel processor, today's best choice for notebooks, which enabled two threads to be fully processed in their own processor cores for truly parallel execution. There are also quad-core Intel processors, which take parallel processing on desktop computers another leap forward, allowing four threads to be processed in parallel. The latest Intel multi-core processors include Intel hyperthreading technology within each processor core, doubling the number of threads that can be processed at the same time. These advanced Intel processors are the preferred processor for desktop users running multiple demanding applications simultaneously, or for running today's multi-threaded digital media applications and gaming titles. It's just one more way that Intel technologies help deliver a great computing experience.
Hey guys, what's up? It's the HD Tech Buzz here today, and I'm here with another Computer Basics episode. Today I'm going to be talking about RAM. RAM stands for Random Access Memory. Alright, so now you know what it is. See you later. Nope, just kidding. I'm going to talk about it a little bit more. I mean, that's kind of obvious. I mean, I'm not going to leave you there. But anyway, if you want to see my previous episode on what is the CPU, go ahead and check it out. Remember, I'll have tons more of these out, or as many as I can think of. So anyway, today, RAM, like I said, Random Access Memory. This allows you to, RAM is like memory that allows temporary data to be stored. So what the heck do I mean by this? Well, this kind of means like if you have a program open, it's temporarily storing the data it's using on the RAM. I know it's kind of hard to explain this. Basically, RAM is like a temporary hard drive, I guess you could say. It's not even so much even a hard drive. I mean, it doesn't store programs. It doesn't store the actual program, the file on the RAM. It stores your actions. It holds open tasks, I guess you could say, open programs and other things running like the system kernel, and I might talk about what the kernel is and something else. The RAM is holding all this temporary data. It's volatile memory, which means that if you turn your computer off, you're going to lose it. So if you have a program open, when you turn your computer off, you're going to lose it, right? It's going to, close out and you're going to have to shut down your computer. Non-volatile memory is like your hard drive, which means it will retain the information even when your computer's off. So that's kind of how I could explain it. I mean, it's volatile memory. It just stores currently open tasks. If you close that program, it's no longer stored in the RAM because it was temporary data. It was an open program. I guess that's how I could explain it. So the more RAM, the more programs you can have open at once. I mean, that's kind of common sense after I just explained that. So my computer has 16 gigs of RAM, and I do this because I video edit. I edit with Final Cut Pro and Adobe After Effects. I use Adobe After Effects for visual effects, which I have a visual effects channel. It's called Plum Puppy Films. Plump Puppy Films. If you want to go check it out, I have a link way down at the bottom of the description and also on my channel of the HD Tech Buzz. And I like this because with 16 gigs of RAM, I can actually keep Final Cut Pro, which is one editing studio, open in one window and Adobe After Effects open in the other. So the more RAM, the more programs, and video editing requires a lot of RAM. The more RAM, the better. Average computers have 4 to 8 gigabytes of RAM. Right now, the standard is still 4 on most. So yeah, like I said, some applications need more RAM than others. Video editing needs more than if you're just checking your email and internet browsing. You know, I said before the average computer has 4 to 8 gigs. 4 gigs is plenty for just checking your email and browsing the internet and doing what an average person would do on a computer. Not programming or video editing or any of that. Now, RAM is clocked at different speeds. There are different clock speeds like 1333 megahertz, which translates to 1.3 gigahertz, and there are 1600 megahertz RAM, and the fastest I've ever heard of is 1866 megahertz RAM. You know, that's pretty much it for RAM. You get the basic idea of what it is. It's in everyone's computer. You need it to run. And that's pretty much it for today's episode. And I hope you enjoyed it, and I hope you know what RAM is now. Don't ask me a bunch of questions that I answered in this video down below, because I won't answer them. I'll tell you to watch the video if I know it's in here. I'll see you later.
Hey guys,
Bye.
What is up? So tonight I'm just going to be making a short video going over the PROM, which stands for Programmable Read-Only Memory. I got a ton of requests to review this, and I think we're just making it harder than it needs to be. So the whole idea of a PROM is that it can be programmed once, and then that's it. We can't program it anymore after that. And basically, once our PROM, when it's working, it controls our processor or our program, really. So let's take a look at this. You may have seen from class that we have like 6 lines going down. Can you see that? Nope. Okay, there we go. And kind of goes like this, right? And then we have our little NOT gate here to account for all of our possible input combinations, right? So that goes down, and then we'll have A, B, and then C, right? And when we have 3 inputs, A, B, and C, then we have a total of 8 possible input combinations, right? Because let's go ahead and look at our truth table. We'll put it over here. A, B, C. We have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. That should be 8, right? 4 plus 4, yep. So that's our 8 possible input combinations. Now we have to put this onto our PROM. So let's draw out 8 lines, because we'll need to implement all of these. So draw it like this. So we'll have 1, 2, 3, 4, 5, 6, 7, 8. Okay, and you remember when we derived SOP expressions from our truth table that we had to, if there was a 1 at 0, 0, 0, then we'd have to say that our function was A naught, B naught, C naught. So here we have A naught, B naught, and C naught. So, okay, so over here we have 0, 0, 1, so we need A naught, B naught, C. So A naught, B naught, C, and then we have A naught, B, C naught. So A naught, B, C naught, and then A naught, B, C. So A naught, B, C, and then A, B naught, C naught. So A, B naught, C naught, and then A, B naught, C. So A, B naught, C, and then A, B, C naught. So A, B, and then C not. And then lastly we have ABC. So A, B, C. Alright. So now that we have that, we need to put them all into little AND gates, I guess, to keep the signal from grounding. Alright, and then we'll draw out our 8 lines a little further. Oh, gotta go farther than that. Alright, and then we can have as many functions as we want. We could have one function, one line coming down all of here, or we could have 2, we could have 3, we could have, or 5007. It doesn't matter. But I think we'd run out of combinations, but still, that we can have as many functions as we want, and your number of bits is the number of your functions. So let's have 8 functions. So we're going to need 8 more lines. So 1, 2, 3, 4, 5, 6, 7, 8. I gotta learn how to draw better. So, and these functions can be anything, and we define them as whatever we want or whatever we're told they are. They can be your output towards a vending machine. I think we did that one in class. Or your inputs to your flip-flops. This could be your input for a D flip-flop, or these could be your 2 inputs for a JK flip-flop. It doesn't matter. It doesn't matter what order they're in. It just matters what the function is, and we can make that up if we wanted to. So let's have our functions. Excuse my voice cracking. I don't know what's going on. Let's call this one D7, D6, D5, D4, D3, D2, D1, D0. This is gonna all go to our flip-flops. It's gonna control our flip-flops. But let's only define D7, 6, 5, and 4. So D7, D6, D5. Nope, I don't think you guys can see that. D5 and D4. There we go. So let's I don't know if I have enough room. So let's make this up. Let's say D7 is just 1 0 1 0 1 0 1 0, and D6 is 0 1 0 1 0 1 0 1. D5 is, I don't know, 1 1 1 1 0 0 0 0, and then D4 is 0 0 0 0 1 1 1 1. So look at this. If we're at address, okay, address bits, okay, words bits. Hopefully that makes some sense. So if we're at address 000, so if we're at address 0 in hexadecimal, well, we know that D7 is 1, so have a 1 right there. And why is my paper so bright? I hope that focuses better. And D6 is 0, right, so we don't touch that. D5 is 1, and D4 is 0, so we don't touch that, and all these are zeros because, well, I didn't define them, so we're not using them. And so our address, 001, so just address 1 in hexadecimal, we have 0, and then 1, so we'll have a 1 right here, and then a 1 again, and then a 0. So for address 2, we have 1, and then 0, 1, 0. And then for address 3, we have 0, 1, 1, 0. And then for address 4, it looks like we have 1, 0, 0, 1. So 1, 0, 0, 1. And then for address 5, it looks like we have 0101, so 0101. And then address 6, we have 1001, again, yep, 1001. And then at address, voice crack again, address 7, we have 0101. So 0101. So that is we just programmed it. So now we have our inputs to our D flip-flops, and again, it can be whatever. They're not always D flip-flops. They can be your output to a vending machine. I could have defined D0 to be your output for the vending machine and made it an entirely new combination, and then we'd have our wires connecting on these intersections. So what can we do with this? Well, you may have also seen from class that we have kind of a multiplexer looking thing, but it's not. It's not a multiplexer. It just kind of looks like that. So we have our inputs, S2, S1, S0, and then we have all of our outputs, 4, 5, 6, 7, 8. This one was D7, D6, D5, D4, and that's all we accounted for, so who really cares what those are? And S2 is our most significant bit, which was A, right? A is most significant. So we have A, B, and C down here. So let's, if we are at address 000, so we have 0, 0, and 0 all going into here, what will our output be? Well, we know our D7 will be 1, D6 will be 0, D5 will be 1, and D4 will be 0. So for our first trial, we'll have 0, 0, 0, and we have 1, 0, 1, 0, and these are all just going to be zeros no matter what. So now let's do the next one. What happens if we are at address 001? So we have 001. Well, our D7 through D4 is just going to be 0, 1, 1, 0. So we're just going to have 0, 1, 1, 0. So let's do the last one now. If we're at address 111, so just 1, 1, 1, then okay. We will be at 0, 1, 0, 1. So 0, 1, 0, 1. And so depending on our input, that's just going to be our output. It's really that simple. And like I said, these could go to anything. These could go to a flip-flop or to some other function that we don't have, or anything. So let's look at the words and the bits. So words are the number of addresses. So we have 8 possible input combinations. So 8 words, right? And we have 8, right? Because I made 8. So we have 8 functions. So we have 8 bits. So 8 words, 8 bits. Can you see that? So that's all that means. So let's make a little table for our words and our bits. So we'll have our address. How do you spell address? That looks right. And then our data. So we have 0, 1, 2, 3, 4, 5, 6, 7. So we should have 8, because 8 words, right? So now we need to look at what data is stored in each row. So we just look at for this whole row right here. So what's the hexadecimal equivalent of all this? Well, our first one, if you don't know, when we convert binary to hexadecimal, we can just look at the first 4 bits to find the hexadecimal representation and look at the last 4. Well, our last 4, see, 1, 2, 3, 4, that's just 0 the whole time, it's only the first 4 that are changing. So I can, I'm not going to write it yet. So let's look at our first 4. Well, we have 1, 0, 1, 0. Well, that's 10 in binary, or decimal. What's that in hexadecimal? That's just A. So we have A0 stored in there. Can you see that? A0. So let's look at address 1. This is address 1, right? Now we have a 0 for the last 4, but the first 4 we have 0, 1, 1, 0, which corresponds to, I believe, 6 in decimal, which is just 6 in hexadecimal. And let's look at address 3. So we have 1, 0, 1, 0, and then the last 4 is 0, so it's just going to be A0 again. So A0. And then 3, address 3, let's, here we go. Well, that's just 60 again. And then 4, well, that's easy enough. Well, actually that's 9. It's going to be 90 this time. And then we will be at 5, so I have 50. And then this one we have, I seem to be missing one. Well, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, 8. Oh, I seem to have messed up. So let me check this real quick. That is 10, so that's correct. 60, that's correct. A0, that's correct. So 60, yeah, and then 90 should be fine. And then 50. Oh, okay, maybe. Okay, I think this is just 90 again. Yep, that's just 90. And then our last one looks like it's just going to be 50 again. So this is our address. If we are at address 0, then that's our output in terms of hexadecimal. So I hope that all makes sense. Thank you for watching. Hope you guys do well on the quiz on Monday, and good luck.